To perform transfer learning, you need three things. First, you need layers that represent your network. Then, you need a data store for your training images, with the labels property storing the correct labels for those training images. And last, you need a variable holding your training algorithm settings. Once you have these three components, training is easy. Just give these three items to the train network function and set it running. When it's done, you'll get back the newly trained network with layers just like the input network, but with updated weights. By default, you'll see a text display showing the progress of the training. Accuracy is the percentage of the training images that the network classifies correctly. You want to see that increasing during your training. However, accuracy doesn't measure how confident the network is about each prediction. The loss is a measure of how far from a perfect prediction the network was, totaled over the set of training images. This should decrease towards 0 as the training proceeds. You may often see the accuracy plateau at its maximum value while the loss value continues to decrease. This is good. It means that the network is still getting better at differentiating between the categories, even if the final predictions may not be changing. You've trained your network and evaluated the performance. Now what? If the performance is good enough, then congratulations! You've made a network that can be put into production as part of your whole application. But often the results you get when you first train the network aren't as good as you need. So what do? Remember that the train network function takes 3 inputs: the network, the training data, and the options for the training algorithm. You can change all of these to see if you get better performance, but you're generally best starting with the options. The learning rate and momentum are the 2 key parameters that affect how the training algorithm updates the weights. Recall that the goal of training is to minimize the loss function, which is a measure of how badly the network performs on the training data. A common way to visualize the training process is to imagine that you're trying to find the bottom of a valley. The height of the ground is the value of the loss function. Your north-south location is one weight value and your east-west location is another. Of course, real networks have thousands of weights, not just 2, but the principle is the same. The gradient descent algorithm works by looking at the height of the ground at a few places around your current position and using that to figure out the gradient or direction that the ground slopes down the steepest. Then you simply take a step in that direction, which brings you to a new set of weight values. But how big a step do you take? The size of that step is the learning rate. If the learning rate is too small, you'll need to take a lot of steps to get to the bottom, and that takes time. But if the learning rate is too big, you might end up jumping around all over the place. If your weights have blown up and your network is giving terrible performance, or even not working at all, the first thing you should do is divide your learning rate by 10 and try again. Gradient descent with momentum tries to stop the jumping around without having to take really small steps. You start off going straight down the direction of the gradient, but at the next step, you don't completely change direction to the new gradient direction, but instead you turn toward that direction, similar to the way you would if you were a mass traveling in your original direction, but now being pulled in the new direction by a force. Your next step is therefore in a direction that's a weighted average of the previous direction and the new direction. That weighting is set by the momentum option. A common problem with all machine learning algorithms for supervised learning is overfitting. This is when your model does well at classifying the training data, but performs much worse on the test data. What's happened is that you've learned the details of the training data set rather than the general patterns. One way to prevent this is to use some of your data for validation. During training, after you've used your training data to update the network, test the network's performance on the validation data. Keep training while the performance continues to improve on the validation set. But once that performance starts getting worse, stop the training because you may be starting to overfit. Use these options to use validation during training.